Hello everyone. In this video we're going to wrap up our introduction to regression by talking about goodness of fit and R-squared. If you've done any regressions before, you've probably heard about R-squared. You may have been told that R-squared is a pretty important thing to look at. The main point that I want to get across here is that R-squared can be important, but a lot of times it actually doesn't really matter. So when you're thinking about fit and R-squared, it's important to think about the context. Let's start out by actually trying to calculate R-squared. To do that, we're going to need to think about some other concepts first. First of those is called the total sum of squares. To calculate total sum of squares, we take each of our individual y's and subtract the average y, square those, and add those all up. What this gives us is a measure of the total variation in our sample. Yi minus y bar is how far does each individual y differ from the average. We square all of those differences, add them up. Notice that this measure has only y's in it. There's no beta hats, there's no x's, nothing like that. Nothing that we can do, running all the regressions that we want to run, will ever change the TSS. It just is what it is. The next thing we need to know about is the explained sum of squares, or the ESS. The ESS is also sometimes called the regression sum of squares, which is a little bit confusing because we already have an RSS, the residual sum of squares. So we're going to stick with ESS for this. The ESS is the total amount of the variation in y that our actual regression could explain. So we take, instead of our observed y's, we take the y hats and see how much those differ from the average y, square those, and add those up. You can think about the ESS as the amount of the variation in y that our regression was actually able to capture. The third type of sum of squares is the RSS, and we've already talked about that in the last video. The RSS is the amount of the variation in y that went unexplained by the model. So if the ESS is the amount that was explained, the RSS was the amount that wasn't explained, these had better add up to the total. By definition, the TSS, the total sum of squares, is the ESS plus the RSS. Remember that when we run a regression, OLS is trying to make RSS as small as possible, and therefore trying to make ESS as big as possible. An OLS regression is trying to pick the beta hats that are going to explain as much of the variation as it can. To calculate R-squared, we take the ESS and divide by the TSS. Since the ESS is always a part of the TSS, the R-squared has to be between 0 and 1. The best a regression can do is explain all of the variation, and the worst it can do is explain none of it. Because of the relationship between these three values, we can also calculate the R-squared as 1 minus the ratio of RSS to TSS. Either way will get you the same answer. To actually calculate this, I'm not going to make you calculate the ESS, RSS, and TSS by yourself, but rather we can actually just get these numbers from the regression output. Going back to the regression that we ran in the last video, we can see up here in the ANOVA table, above the main regression table, we have three rows here: regression, residual, and total. The regression sum of squares, so we look at the SS column. The regression sum of squares, that's our ESS. The residual sum of squares, that's our RSS. And the total sum of squares is our TSS. To calculate the R-squared, we can take our ESS and divide it by our TSS, and we get 0.92 in this case. We can scroll up here and see that we actually get the R-squared in the regression output, and we can see that we can confirm that with our own calculation. Let's talk a little bit about what R-squared actually tells us. A high R-squared means that our regression was able to explain a large amount of the variation in y, whereas a low R-squared tells us that there is a lot of variation out there that we weren't able to get at. If our goal in running the regression is to try to make precise predictions about exactly what y is going to be given a certain x, then R-squared does matter to us. Making accurate predictions will be easier if we have a model with a high R-squared. But if we're trying to answer a little bit of a different question, that is, does x have any effect on y, that is, when x changes, how much will y change, the r-squared doesn't actually matter because we don't actually care about the precise value of y. We're just thinking about a change in x and a change in y. To get at that question, we're going to need to do a little bit more work, which we'll come to later on. For right now, what I want you to think about is that if somebody is trying to convince you that their regression is the best regression because of its high r-squared, you need to think about the context that we're working in. If they're trying to make that claim while having this causal interpretation, that's simply not correct. If what they're trying to do is make precise predictions about actual values of y, then that argument has some merit. To think a little bit deeper about r-squared, we're going to run another regression. We're going to load up a new dataset called house price. In this dataset, we've got prices and some characteristics of houses that were up for sale in Boston, Massachusetts. We're going to use multiple regression to estimate the following equation. We got price equals beta naught plus beta 1 lot size, so that's the square footage of the lot the house is on, plus beta 2 times the number of bedrooms, plus beta 3 times the number of bathrooms. And then we're going to calculate the r-squared. Over here in Excel, we're going to go back to Data, Data Analysis, Regression, and select our Y range, our price. And for the X range, we're going to select lot size, bedrooms, and bathrooms. Make sure our labels box is checked, and click OK. We'll zoom in here to take a look at our estimated equation. What this tells us is that for every square foot of lot size, we get a higher price of about $5. For every bedroom, about $6,500, and for every bathroom, about $18,000. Some students in the past have wondered about, well, why is there a negative number here for the intercept? And my answer to that is, first of all, intercepts can be negative. Don't worry about that. Of course, a negative price for a house does not make any sense, but also, we would only get a house price that has this price if all the rest of these were zero and blanked all these out. But that's also not realistic. Every house has at least one bathroom and at least one bedroom, so that's already going to be way more than negative 2,300. Let's go back up and look at the r-squared. We can see that about 47% of the variation in these house prices can be explained by lot size, bedrooms, and bathrooms. So just under half. What I'm going to do now is go back to our dataset and take a look at these 6 other variables that I have in the dataset. x1, x2, x3, x4, x5, and x6. I'm going to now add those variables into our regression. I'm going to keep the y range the same, but for the x range, I'm now going to select everything we've got. Lot size, bedrooms, bathrooms, plus our 6 new variables. And run this regression. What do we notice about the r-squared here? Well, it's gone up. It went up from 47% up to about 48%. So is this regression that we've just run better than the regression that we ran before? Well, I can pretty definitively tell you the answer to that is no, because I created those variables with a random number generator in Excel. And by adding those random numbers into our regression, we were able to increase the r-squared. So obviously we know that a bunch of random numbers that I created 30 years after this data was collected had nothing to do with the actual house prices. So why does the r-squared go up? When we add a new variable to a regression, worst case scenario is that this variable has absolutely nothing to do with the outcome, adds nothing to the regression, we get a coefficient estimate of 0, the r-squared stays the same. Adding another variable could never make the r-squared any lower, but chances are, even a completely random number will just by dumb luck pick up some variation in y. Maybe not a lot, but just a little, and I did that 6 times, and that just picked up a little bit more of the variation in y. Does that mean that the second model that we did was any better? No, of course not. So when you're thinking about r-squared, recognize that it has value in certain situations, but it's certainly not the be-all and end-all of deciding which regression is the best one. This brings us to the end of the first set of slides for regression. What we've done here is covered the basics. We've talked about what is a regression, we've talked about how we run them in Excel, but also a little bit about what's going on mathematically. how Excel is using ordinary least squares to get the estimates that minimize the RSS. And then finally, we talked about how to calculate R-squared and what can we do with it. If you have any questions, feel free to let me know. Thanks for watching.